Let's now solve for the electric field produced by a ring of charge that is centered on the x-axis. The whole ring has charge Q, and as before with a finite line of charge, we have A and minus A. So A is the radius of the ring, and out here at point P along the x-axis, we're going to determine what the electric field is. Well, let's consider a differential element of this ring. So we'll call that ds, differential arc length, right? And dq, uniform linear charge density along that ring. So dq is this little element here of ds. And the distance to P, we'll call that r, and we have theta. So r is square root of a squared plus x squared. We've seen that before. Producing a differential electric field at point P, shown as given. And we have the x component, and we have the y component. And there's angle theta again. All right. Now, we have another ds dq diametrically opposed to this first one. We'll consider it a complementary pair. And we can produce on the diagram the electric field produced by that, same as the other one, just in a different direction. So we have the x component and we have the y component. And from symmetry we see that every single ds dq, every dq along this thing, around this thing, has a corresponding pair that is on the opposite side, so that in the y direction the electric field is 0. Because of symmetry. So that's going to make this analysis really easy, way easier than what we did with the finite line of charge, as you'll see momentarily. So we have here then the total electric field from the two differential charge elements that we just considered. So now, what is that differential electric field? Well, it's K Q over R squared. So there it is. But we're interested in the x component, so that's dE cosine of theta, which is K Q over R squared, cosine of theta, which is x over square root of x squared plus a squared. So that's K x dq over x squared plus a squared to the 3/2. So now that we know what the differential electric field is from a dq, let's find the electric field in the x total. So we're going to have to integrate the differentials. So that's the integral of x dq over x squared plus a squared to the 3/2. But notice that x is constant. X is the same value as we integrate completely around the ring. So fortunately, since a is a constant, x is a constant, we can bring this whole thing outside of the integral. So e is equal to k x q over x squared plus a squared to the 3/2. Now, how did I just write q there? Because this was dq. Oh, the integral of dq. Add up all the dq's around the entire ring, and of course you get q. So we've really just solved the problem. There it is. That's the final answer for the electric field from a ring of charge. Of course, assuming that you are considering that point being on the axis of symmetry, right through the center of the ring. Now, if x is much greater than a, well, then the a component essentially goes away. X squared to the 3/2, x squared to the 3/2, but x up here, so gives us x squared as the result. And as you would expect, it looks like a point charge when you're a long ways away. So that analysis was far simpler, I'm sure you'll agree, than the finite line of charge. Let's move on. So, the disk of charge. Now, we just did the ring, and you're going to see that there is a very close and marvelous connection between a ring and a disk. And by the way, this is uniformly charged. It's a uniform charge distribution on the area of the disk. So here's the disk, and this part here, this red ring, is exactly that. It's a ring. And it's dq, the entire thing is dq, and differential area. So this is an infinitesimal ring that makes up part of the disk. So the disk radius is r, and the particular ring of charge dq is at radius little r. So that's the variable. Well, the electric field at point P. We already know what the electric field from the ring is. That's what we discovered here. Now, the big idea about this disk of charge is the disk can be modeled as an infinite number of those rings concentric with each other. So we're going to just apply this idea, and basically now we have to integrate again. We have to integrate all the contributions to the electric field of the potential infinite number of rings of charge of infinitesimal width to get the entire effect of the whole disk. So it sounds hard, but it won't be because we've done most of the work already. So differential area of that ring, that's simple. The circumference times the width. Well, the width is differential r. The circumference is 2 pi r. So 2 pi r dr is dA, differential A. And now we offer yet another definition that you're going to love. You've already now been introduced to linear charge density, lambda. Now check out surface charge density, sigma, which is charge per area instead of charge per length. So that's dq over dA. The differential charge over the differential area would be sigma. That's going to be nice. For the ring then, we have differential E in the x is k x dq over x squared plus a squared to the 3 halves. That's the differential EX. So we're going to have to, as I already mentioned, integrate those and discover the entire effect of all those concentric rings. Let's do it. So the differential EX was basically k x dq over x squared plus r squared to the 3 halves. So what am I putting all this? There's the x. Here's the k and the x. dq, oh, dq. Well, dq is sigma dA. dA was 2 pi r dr. So there's sigma times dA, which is dq. All right, fantastic. And you're getting a hint right now, even though you don't really know why k is 1 over 4 pi epsilon 0. You kind of see a connection here at this juncture of some simplification. But there's perhaps a deeper connection that we'll see a little later on. Nevertheless, let's simplify this then. Well, before we simplify, to get the electric field, we bring out the constants, 2 pi sigma x over 4 pi epsilon 0. Integral 0 to r of r dr. R dr over x squared plus r squared to the 3 halves. Pi's gone. From the tables, we see that this integral form takes on this result. So let's just go ahead and apply that. So EX equals, there's the negative, bring that out. Here's the constants that are left, and 1 over square root of x squared plus r squared from 0 to r. So we're going to integrate from all the way across the entire disk. Negative sigma x over 2 epsilon 0. Plug in big R for little r. We get that minus this result. So let's flip the signs around, and we get this result. Notice we have x here and 1 over x, and so let's go ahead and bring that x inside, so to speak, and we get this simplified version right here. And that is our very beautiful, simple little result, even though it looks kind of like somewhat like a pliosaur. Well, maybe a stegosaur, I don't know. Some kind of dinosaur. Anyway, that will be our probably simplified result, as simple as we can make it, for the electric field from the disk. Well, as we often do, when we derive a general result, we let one of the variables, say, go to infinity. In this case, we'll let the radius go to infinity and see what result we get. And it's not just of an academic exercise here. The approximation of infinity is actually a good approximation in certain situations. I'll reference our computers again and the microelectronics and capacitors. So here is our disk going to infinite radius, and we put a ring of charge within it, and sigma is constant. The quantity 1 over r squared over x squared plus 1 is what we derived before from looking at the finite disk situation, the stegosaurus. And so what happens when r goes to infinity here? Well, this whole thing goes to infinity, and it goes to 0, which is very wonderful because that stegosaurus had its complexity because of this term. And so for an infinite disk, we have the electric field being sigma over 2 epsilon 0. That is extremely simplified. And as I already alluded to, for instance, in computers and capacitors, we have charge distributions that at the dimensions of the other circuitry that could be affected by that charge distribution, you're really very, very close. The dimensions are very small, so from that standpoint, reasonably, say a square centimeter looks like an infinite sheet or an infinite disk. Now, let's extend this just a little further. The sheet of charge, which is really what this disk is, a disk and a sheet, the same thing. Well, that's not exactly true, but I will clarify that at a later point when we study capacitors. So we just learned for an infinite sheet, or disk in this case, we have the electric field being sigma over 2 epsilon 0. So let's consider this sheet charged positively. Well, let's put 2 parallel infinite sheets together, each one having their charge sigma, but they're equal and opposite. This is actually the situation that we have for capacitors. So we have plus and minus sigma for the surface charge densities. Now I'm going to express the electric field in all of space for this sheet of charge. The electric field goes toward the negative, so on this side, toward the negative. Ignoring this for the moment and just thinking in space way out here, the electric field is toward the negative. So all those green vectors correspond to the electric field associated with the sheet of charge having surface charge density negative sigma. Let's do it for the positive sheet. The electric field goes away in all of space. And since it's constant, since there's no divergence of the electric field in space because of the sheet characteristic, we have the electric field way out here is likewise constant, the same value. So we can figure out what the electric field is on this side, above the whole thing. If you add the vectors, 0. Below, underneath, you add the vectors, 0 electric field. But what happens in the middle? Well, the electric fields add to give a larger electric field. Now, that's sigma over 2 epsilon 0 twice, which gives us the electric field from 2 parallel infinite sheets of charge, which, by the way, is a capacitor, and that's sigma over epsilon 0. A marvelously simple result. It just gets simpler all the time. And this really has practical significance. So these two expressions, you're going to want to know these. You'll use them, so you will probably learn them in spite of yourself. And to distinguish one from the other, one is 2 sheets together, and the interacting electric fields producing an electric field between them that's double what you would get from a single sheet.